Good afternoon. Today I'm going to talk about Artwork's SFGEN program, which is designed to prepare a GDSII layout for fast rasterization, and it can also apply a number of compensations. We're going to focus today on edge compensation, which is the ability to take your data, size it by shrinking or expanding it by a certain amount along the edges. The reason we need to do this has to do with the fact that when you rasterize this, your grid is much smaller than your laser beam, so half of your laser beam can potentially lie outside the area that you want to image, and that will result in wider lines and narrower gaps. So let's go over to the SFGEN program and see how that works. We'll start SFGEN by opening a file, and the file we're going to open is this 300mm test wafer, which you just saw. It'll get scanned, and when it's been accepted, it'll let you know. You can select one or more layers. Let's go to the advanced dialog. Here we set the number of threads the program can use. Some of the critical steps can take advantage of as many cores as you have on your computer. And then we're going to treat this as if it were what we call LCD data. We have to set a couple parameters here, setting a span length of 25,000 microns and a vertex count of 200,000. The next tab has our transformations. I'm not going to do any transformations except for sizing. The one we care about is the edge offset. We're going to reduce the edges by half a micron on all sides. We picked that value because we're assuming that our laser beam is on the order of 1 micron. If we shrink everything by half a micron, then the laser beam will stay inside the original shape. So let's go ahead and run convert on this. First it opens the file. Now it runs a pattern recognition routine that looks for repeating patterns. Now it's actually looking at the individual structures and processing the structures and their children. This program takes advantage of repeating data. Most of your large panels consist of a small circuit that's been repeated hundreds or even thousands of times. If you know that, you can avoid doing a lot of things by brute force. The data that's not repeating we call the frame. We have to process that brute force, which is what's going on right now. Once the frame is done, we'll be able to merge the results of both the step data and the frame data. Then we'll have our final output. All right, it's finished. Let's check to see how long it took. According to the log file, it took 5 minutes and 14 seconds total. Almost all of that time, as you can see, was processing the background data. This file had a lot of background data because we did a round clip to the edge of the wafer. All of the cells that were near the edge were exploded, and so that generated hundreds of thousands of polygons. The rest of the time was only a few seconds. Now I'm going to use Artwork's merging tool to merge the input file, and we're going to merge the output file, one that's called out, and we'll merge and view. Now they've been combined, and now it's reloading the combo. So let's zoom in somewhere tight here. Zoom in this area here. And let's turn our fill off. Continue to zoom in. Now we can see the results of the data being sized down. So the gap goes sized up, and then the actual data lines are sized down. Let's find a data line over here. The original is the blue, and the size data is the cyan. If we measure this, let's measure the original data. And it's telling us that the distance is 2 micron, which is what we expected. And now let's measure the new data, and it's telling us the distance is 1 micron. So we got a half a micron on each edge. When we put the beam here, we'll end up getting the width that we wanted in the first place. You can see that the sizing works. It's a fairly compute-intensive process, so it should be done offline prior to rasterization.